Everyone, today I'm going to be talking about halide functional groups. To begin, let's look at a comparison model. Halide functional groups can be thought of as prefixes in English. Like prefixes, they come attached to the word or chemical compound and change the meaning of the word or the chemical properties. Also, like prefixes, the same halide can be attached to many different compounds, but it will always have the same general effect. For example, chlorine can be attached to an sp2 hybridized carbon or an sp3 hybridized carbon, but it'll always be a chlorine atom that increases bond strength. Like chlorine, anti can mean antisocial, anti-gravity, antibiotic, or many other words, but it's always going to have the effect of meaning against. Next, let's look at the first of three types of halides, the alkyl halide. Alkyl halides, also known as haloalkanes, consist of an sp3 hybridized carbon attached to a halogen. The halogen is seen here as an X, and this X can be fluorine, chlorine, bromine, or iodine. The specific sp3 hybridized carbon in alkyl halides is also known as an alkyl group, which is formed by removing a hydrogen atom from an sp3 hybridized carbon. Further classifications within the alkyl halides are the primary, secondary, and tertiary alkyl halides. For example, ethyl fluoride, seen here, is a primary alkyl halide because it has one single alkyl attached to the carbon. In general, alkyl halides increase the boiling point of a compound because they add electrons, which increase the size of the temporary dipoles in van der Waals forces. Boiling points also rise as the attractions become stronger, meaning it takes more energy to overcome them. As for solubility, the alkyl halides are relatively not soluble. They're at best only slightly soluble in water because the dispersion forces and the hydrogen bonds must be broken in order for the haloalkane to be soluble. As seen in the graph here, bond strength increases from the bond between carbon and iodine to the one between carbon and fluorine. Therefore, reactivity, or how easily the bonds are broken, increases going from the chlorine-fluorine bond down to the chlorine-iodine bond, because stronger bonds are harder to break. Next, let's look at the second type of halide, aryl halides. An aryl halide, or haloarine, is a functional group in which one or more halogen atoms are bonded to a benzene ring or another aromatic ring. For example, bromobenzene, seen here, is an aryl halide because bromine is attached to an sp2 hybridized carbon. Interaction between the delocalized electrons in the aromatic ring and one of the lone pairs on the bromine atom causes the structure to change, as seen here. The delocalization introduces additional bonding between the carbon and bromine, which makes the bonds stronger. As the halogens increase in size from fluorine to iodine, the boiling points also increase. As for solubility, aryl halides are insoluble in water because the molecules are quite large. The strong dispersion forces and many hydrogen forces would have to be broken, so it's unfavorable for halogens to be soluble in water when they're in aryl halides. The third and final type of halide is an acyl halide. The general structure is seen here, where a halogen atom is bonded to a carbonyl carbon. An example of an acyl halide is a propanyl chloride, as seen here. Acyl halides are generally fuming, colorless liquids, and they do not dissolve in water. In fact, when acyl halides come in contact with water, they often react violently to produce carboxylic acids and hydrogen halides. As seen in both alkyl and aryl halides, acyl halides increase the boiling point of a compound due to the addition of electrons. They are also extremely reactive, often producing acidic fumes. The example here depicts the nucleophilic acyl substitution reaction between ethanoyl chloride and a hydrogen halide. Moving on to naming organic compounds with halides. After determining the root name, seen here, based on the number of carbon atoms in the longest carbon chain, you have to look at the specific halogen present, which determines the group name or prefix. Then you look at the ane, ene, and ine classification based on whether it's a single bond, double bond, or triple bonds are present in the carbon chain. Then, if there's more than one halogen, you add a prefix, as seen here. These prefixes are numerical, and they go in front of the halogen prefix. Additionally, you have to see the location of the halogen atom on the carbon, and this can be seen by a number, such as if the halogen is attached to carbon 1, then you have 1 fluoromethane, for example. Next, we can move on to the applications of halogenated compounds. Some common examples are methyl chloride, methylene chloride, chloroform, and carbon tetrachloride. Methyl chloride is a gas at room temperature, while the rest are liquids. Chlorinated compounds are great solvents for nonpolar solutes that would dissolve in hydrocarbons because they are less volatile and flammable than hydrocarbons. Chloroform and carbon tetrachloride react with hydrogen fluoride to form chlorofluorocarbons, or CFCs. These are sold under trade names such as Freon and Genetron. Freons are inert gases with high densities, low toxicities, low boiling points, and no odor. Therefore, they're extensively used as propellants, both in hairsprays and antiperspirants. However, the role of CFCs in the depletion of the ozone layer, depicted here, has led to their ban of use in aerosols by the Environmental Protection Agency, or EPA. Unfortunately, some CFCs are still used as refrigerants in the air conditioning industry. More complex halogenated compounds, such as halothane, thyroxine, DDT, and chlorine, also have extremely important applications. Halothane, seen here, is an inhaled anesthetic that reduces blood pressure, depresses respiration, and decreases pulse rate. This induces muscle relaxation and reduces pain sensitivity by altering the tissue excitability. Thyroxine, seen here, is a hormone secreted by the thyroid gland, and it plays a vital role in digestion, heart and muscle function, brain development, and the maintenance of bones. DDT, seen here, is an insecticide that was shown to accumulate in the fatty tissue of birds and other wildlife, causing liver cancer. In 1972, DDT was banned by the EPA. The last one, seen here, chlordane, is a potent insecticide that was used to control termites until it was banned by the EPA in 1988. So that's it. Thanks for listening.